All right, perfect. So today we're going ahead and finally moving on from how do I get the derivative to why do I care about the derivative? What can I do with the derivative? How does this apply to what I may be doing in the future? So in particular, today the focus is primarily going to be in physics. So uh, just before I actually start introducing some concepts, how many of y'all in here have taken some type of physics class, anything like that, where you did something like maybe talking about gravity or throwing something off? What was that? Yeah, a lot of y'all are probably taking that. That's pretty standard, people taking physics. Yeah, so a lot of times before calculus, if you took physics before calculus, you probably did trig-based physics. And a lot of time whenever we talk about physics, we like to say we either do trig-based physics or we do calculus-based physics. If you're engineering, more than likely you're doing calculus-based physics, and that's exactly what we're going to be doing today. We're going to talk about how does the derivative and what we know about the derivative apply to physics and some applications. All right, so um, let's go ahead and start. The first thing I have here is discussing two-dimensional motion. So can someone tell me what does it mean by two-dimensional, more or less? Yeah, whenever I talk about two-dimensional, another way I might say this is along a line. So like, for example, if y'all were observing me going to the right and then to the left, then you'd be describing my motion basically in two dimensions, more or less. I am being a little bit sparse on this two-dimensional phrase. Um, so let's suppose my particle moves along a straight line. Then the position function, we often use the notation s for position. And that's some function that's based off of time. That's why it's f of t. So my position is based off the time. And this position function, well, it gives me the exact location of my particle. And here I'm saying particle, but it could generally just mean any object. But particle, we're being a little bit exact. So imagine we're thinking of a particle, and we can say, imagine it's moving left and right. Or we can say up and down, for example. I guess it would be more accurate to say one-dimensional movement. Perhaps I need to change that later. So we have position function given by an s. I'll give y'all some time to copy this down. So in other words, if I'm thinking about a particle moving along a line, it might be going this way, and then sometimes it goes back this way. This position function, based off the time, it'll tell us exactly where it is. And we're going to see some examples in just a moment. But again, I want to emphasize, we are only looking at my particle along a line. Bless you. All right, so I'm not changing the slide. If I did this right, it should pop up more. So here I have a function that's mapped out. Here I'm calling it my s and my f of t. The first thing I want to note here is that notice that my x-axis, well, what we would usually call my x-axis is for t. I'm using the variable t for time. Because we're doing an application, we want to see how my position changes in respect to time. And then my vertical axis, s, this is telling me my distance from my starting point. So I want to talk about what does it look like is happening here in this graph for the particle. So at time 0, I'm at my starting point. I'm not far from my origin. Yeah, we can imagine that it starts moving away from my starting point, but then it starts to slow down almost to a stop. So if I was doing this, imagine that I'm walking along a line. The way I would model this is that here's time 0, and then I'm walking away from my point, eventually slowing down up to a certain distance. That's how I'm describing this is describing my particle motion. I want to emphasize that this is not how I'm moving. I'm not moving in a curve. This shows me how far am I from my starting point. So like, for example, if I put right here, this means I'm 1 away from my starting point. Here, I'm 2 away, 3 away, 4 away, so on and so on. So here, just again, restating that, the graph given on the left may be used to describe an object that I pushed forward, and then it sort of eventually comes to a near stop, kind of like what I did whenever I walked over. I start walking, eventually slowing down, let's say at this desk. All right, so we have an example of a position function. And one thing I'm going to note for today, the instructions are going to look like they're really long. It might be better for y'all to reference, if you can't copy it all down, to reference the worksheet on Blackboard that I posted. Or if you're watching the video later on, you can always pause the video to read through this as well. So I have a position function. What other aspects of particle movement would I be interested in besides where my particle is? The speed, right? How fast is the particle moving? You can imagine that this is a car. If I'm tracking a car, I care about where is the car, maybe how fast is the car moving, for example. And that's actually going to lead us into our next function in just a moment. You can still see a couple of people copying this down. I'll give you all some time to copy this before I move on. Does anyone happen to know the word or term that we use? Not really speed, but a more accurate velocity. Yeah, we're going to talk about what is velocity, how's it related to position. We're also going to talk briefly, how is velocity different from speed? All right, does anyone still need some time to copy down this slide before I move on to the next? All right, so I think I might have one small thing here. Let's talk about displacement. Displacement of a particle refers to my net change, if you want to think about it this way. Where did I start and where did I end? So displacement of a particle from time A to time B, this is given by, and this triangle is a delta S is equal to my final location minus my initial location. We can call this my displacement or my net change if you want. This little triangle, again, it's a capital delta. We often use a capital delta in math and physics to mean the change. So this is my change in position or net change. Displacement is nice to think about, but it does have some weaknesses. Again, if I want to talk about displacement, I start on this, I'm standing on a group of red tiles right now. I might move forward this way, then I turn back a little bit, maybe go back some more, and then go back. My displacement would be how far am I from my original position? That is my displacement. The thing about displacement, it doesn't tell me, did I go back and forth? It just tells me where I started and where I ended. So displacement is nice, but we're not going to often talk about it. Mainly because we want to know, how did my particle end up at that spot? All right, so I have displacement. And we are going to be introducing a lot of new notation today for all of these. We have S for position, and then we have this delta S for change in position, or you can say displacement or net change. All right, so now we can finally move on from here. Let's go ahead and talk about velocity and speed. How are they similar? How are they different? So if I have a position, again, we know position is denoted by S. The velocity function, which we use V for velocity, is the derivative of position in respect to time. Or often you're just going to hear me say, how do I get velocity? Well, it's a derivative of position, the position function, to be exact. In other words, if I want my velocity function v of t, this is the derivative of position. Or if position is given by f of t, it's f prime. Again, to get velocity, you take the derivative of position. So it's a derivative of position in respect to time. Remember that this bottom tells me what am I taking the derivative in respect to. Remember how before we had dy dx? Before we're doing the derivative in respect to x. Now we're doing it in respect to time because we're doing an application now. And the most common thing about it is checking it in respect to time. And then we can also talk about speed. How is speed different from velocity? Well, in terms of calculations or formulas, the speed is the absolute value of velocity. That is, speed is equal to the absolute value of v of t, or you say the absolute value of the derivative of position. These are all equivalent formulas down there. So looking at these two terms, velocity and speed, what are some differences that I'm noticing between velocity and speed? Let's talk about the first one in terms of numerical value. What could be a difference between the velocity and speed? Yeah, velocity could be negative, and then velocity could be negative, speed must be positive, or if I want to be more accurate, non-negative, because we could have zero speed. But the question now is, what does it mean to have positive velocity versus negative velocity? And which one of these sort of relate more to what we do in real life? Yes. So the sign of velocity, positive or negative, refers to the direction of travel. So I'm going to have to repeat this probably to really get it in. So here's my starting position. I'm standing on a red tile to the left of the screen for y'all. If I am walking this way, away from my starting position, then I can say I have a positive velocity. But if I'm walking back this way, I have a negative velocity. Or if, to be exact, if I keep on walking this way, I continue to have a negative velocity. So the sign of velocity helps me decide the direction of travel. So whenever we're talking about cars, whenever you're looking at the dashboard of your car, those numbers that you see, the miles per hour. Yes, so the miles per hour that you see on your dashboard, that refers to speed. Because you're not going to see on your car that you're going negative 20 miles per hour. You're just going to see that it says, yeah, you're going 20 miles per hour, for example. The reason is that there's not really a good way for us to check on a car about are we doing positive velocity or negative velocity, because that would mean that you had to set to identify a starting point, for example. And again, the sign of velocity is based off, am I going in the positive direction or in the negative direction relative to my position? So we're doing a combination of calculation, computation, and then application. So we're combining all these concepts together. So we have velocity and speed. There's one more aspect of particle motion that I want to talk about. We have position, we have velocity. So one position tells me where is my particle. Velocity tells me how fast is my particle moving. What is a third thing? Can y'all guess a third aspect that I would care about? What was that? Yeah, acceleration. We're going to talk about how fast am I speeding up. If I'm using the example of a car, are you slamming on your gas or are you just slowly tapping it to go faster, for example? So let's talk about the last aspect, acceleration. The acceleration function refers to how fast is my velocity changing. In other words, how fast am I speeding up or slowing down? So we use A for acceleration. This happens to be the derivative of velocity. So why is this the derivative of velocity, by the way? Well, first off, position, you might measure this in, for example, miles. How far are you from a certain location? Since velocity is how fast is your position changing in respect to time, you might measure your speed or velocity in miles per hour. Whereas your acceleration, we might measure this in miles per hour, hours squared. And we'll talk about that more in a second. So if I have a position function, acceleration is the derivative of velocity. But since we know velocity is a derivative of position, we can also say acceleration is the second derivative of position. That is, A of t is d2s dt squared. I take the position function, do the derivative twice in a row, and I have acceleration. So I'll give y'all some time to copy this down as before. So far we've really introduced four concepts of position, velocity, and speed, and then acceleration. All are closely related to each other. One thing I will note is that all of our theory right here is based off, do we know the position or do I know the velocity? Because if I know the position, I can get velocity and then I can get acceleration. So right now we've been pretty much giving these definitions. We're going to do an example so that we can really try to get concrete examples down. And one other thing I'll note about this before I move on to the next slide, the acceleration is also something that you see on your car dashboard, typically on the right side. So for most cars, you tend to have your speed on the left and then your acceleration on the right. I guess unless you have a digital speedometer. All right, so let's go ahead and do an example if I time this correctly. Oops. This is one just a recap of everything that we covered. Position, velocity, acceleration, and speed. Position is S, velocity is V, acceleration is A. Speed, we don't really have a special term for that. I just use speed. And what I have here on this third column is what I was mentioning earlier. Position, I might measure that in feet. Velocity, I might use feet per second. acceleration feet per second squared, and then speed is still feet per second. Again, this comes from the fact that we know our relationship with the derivative. How fast is my position changing in respect to time? In other words, how are my feet changing per second, for example? All right, so this one's just a nice thing to keep in mind. I'm going to go ahead and move on to this the example one finally. All right, so example one. Suppose that I'm talking about the motion of a soccer ball after t seconds. I think this should be one-dimensional motion the more I think about it, but I'll have to think back on it. That's given by this position function. S is equal to f of t, which is equal to 14t minus 2t squared. So this function tells me the position of my soccer ball for t being between 0 and 9. And I'm going to say that my position is measured in feet. And if I have a positive s value, this corresponds to the right of the origin, or the right of my start point. And I went ahead and graphed this for us. This is what 14t minus 2t squared looks like for us if I graphed it. So first off, for part A, determine and graph the velocity function. And then I want you to describe the motion of my soccer ball along this line. So let's see if I have any space up here. Let's start off with the first part of part A. Determine the velocity function v of t. So I'm going to write it up here since I don't really have any space. How do I get the velocity function again? How do I get velocity based off what I'm given here? Yeah. So yeah, to get the derivative of, to get velocity, we just need to take the derivative of position. So here's position, right? 14t minus 2t squared. I just needed the derivative to get velocity. So what's the derivative of that s function? We should be getting, I believe, 14 minus 4t. Because I just took the derivative using power rule here. Derivative of 14t, we get 14. Derivative of negative t, 2t squared, I get minus 4t. All right, so I have the velocity function. We're done with that part, for at least the first part of part A. All right, and then I want to go ahead and graph the velocity function. Does anyone know what this graph looks like? 14 minus 4t. Yes, with the shape of the graph here for 14 minus 4t. Let's see. The way that I can think of this, this looks a lot like y equals mx plus b, right? So this actually turns out to be a line that goes downwards, and I'm going to show you in just a moment. Let me clear this. I'll rewrite this in a second. Let me see if I have the space. Here we go. So part A, I just rewrote the function because that's what we care about, and then this graph. So we had the velocity function. We said v of t was, actually, let me see if I animated this. I did not. I'll rewrite it. We have v of t was 14 minus 4t. And as it turns out, the graph of this looks like a linear function going down. It hits my y-axis, or in this case, my v-axis at 14, and it goes a slope of negative 4. So this is what my velocity function looks like. So now the question I have here is I have my velocity function and I have my velocity graph. Using this information, I claim that we can determine how is my soccer ball, the particle, moving. And actually, we don't really need all of this information, really. I would say the position function would be enough for me to determine how this is moving. But it helps to see the velocity as well and how everything is related. And I'm pretty sure here I do have my animation for us. So I'm going to clear that V of t. So looking at this position function, can anyone sort of describe what is the motion of this soccer ball along a line? Let's say I'm starting right here on this tile. And let's say that this is the positive direction, and then this is the negative direction. So based off this position function, can anyone describe to me or have a guess on how is the soccer ball moving? Yeah, so if I think about this, this means I'm here, I'm at my starting point. I'm only moving in a line. Whenever my position is positive, this means I'm moving in this direction, away from the start. But then my position starts going down, right? Meaning I start returning back. And I'm going to have an animation for this in a second. And then I keep on going up to a certain point. So let's see, hopefully this animation works. Here I have a soccer ball, right? And I put these red dots on the graph to show you how does it correlate at one point to another. So again, let's say that this is the positive direction, this is the negative direction. So as my distance increases, it's going to the right. And notice my velocity is getting lower as I get there. So I hit this peak here. I went all the way to the right. And then what do you think is going to start happening after this? Yeah, it starts going back, right? The question I have here as a side topic is my velocity at that point is 0. Can anyone give me an idea why is my velocity 0 when I start to turn around? What was that? Yeah, exactly. Because whenever you turn around, you can't just go automatically. There's a brief moment where you do have to pause, for example. So this is at that point. If I keep on going, it goes back. I hit back to the center, and then it keeps on going this way. This is how I'm relating it. Other things I want y'all to notice. When the velocity was positive, it was going in the positive direction. But once my velocity turned to negative, it started going in the negative direction. Let's see if I can go back. So again, we start at the center. Positive velocity means it moves to the right. It has to turn around, so it hits 0 velocity. And then the velocity turns negative, meaning it goes back in a negative direction. This is how my two things are being related to each other. All right, so looking at this, I can go ahead and give my final answer for part A. Again, we had the velocity function already. This was, what was it, 14 minus 4t. And then we wanted to see when is it moving left, right, or stationary. So based off of that, when was it moving? Let's do to the right. During what times was it moving to the right? In that animation, when did my ball move to the right side? Well, let's see. I started off moving right. So I can go ahead and say, let's start off with 0 seconds. When did my ball, how many seconds later did my ball turn around based off this velocity graph or the position graph, whichever one? Well, we know that we turned around at that spot, right? When my velocity was 0. That's when I started to turn around. Or we can see here, this is me moving to the right. Positive means I move right. And then here I started to move left. So we just got to figure out what is this point right here. What is my velocity at that point? 0. So really, if I want to see where I turned around, I have to see when is my velocity 0. Here's my velocity. I want to see when is it 0. This one, I can solve this pretty quickly. I can add 4t, for example, and get 14 is equal to 4t, and then divide by 4. So here I get, let's say, 14 over 4, that's 7 over 2, or 3.5 seconds. And that's actually going to give me the information I need to know when I turned right. I know at 3.5 seconds, I had to pause for a second. And I know I was moving right from the start. So I was moving right from 0 to 3.5 seconds. After that, I started moving left. So for left, I started moving left at 3.5 seconds. And how long do I move to the left based off this picture? What is the end of my time observation? 9 seconds. So again, what we said here is that for 3.5 seconds, I was moving right. And then I had to turn around at 3.5 seconds. And then I started moving left all the way up until the end of my time observation, because I was only watching for 9 seconds. So we just described the motion of the soccer ball relative to the origin. All right, so there's a lot that was going on here. Any questions about this part A? We're not going to do part B today because part A is already a lot to first start off with. The things I want to point out here, again, positive velocity means that I'm moving in the positive direction. Negative velocity means I'm moving in a negative direction. And if I ever want to turn around, that means there has to be a point where my velocity is 0. You can imagine if I'm walking this way and I want to turn around, I had to take a very split-second pause to turn around. So we've worked with velocity, and now we can describe how a particle moves left or right. Yes. The whole left, what? Okay, this just means the time that I'm moving left. So 3.5 seconds to 9 seconds, that's when I'm moving left. Because we saw this earlier. Do you mind if I erase this to go back to the animation? Yeah. Let me do this. So this is 0 seconds, right? I moved to the right until I hit 3.5 seconds. I know that's when I paused because that's when my velocity is 0. because velocity 0 means I'm not moving. And then 3.5 seconds all the way to the end, I can see that I'm moving to the left. So that's what that 3.5 to 9 was saying. From 3.5 seconds to 9 seconds, I was moving, this ball was moving to the left. And remember, this position is telling me how far am I from the start along this line. So like whenever I was all the way up here, this means I'm somewhere to the right, I'm somewhere to the right. All of a sudden I'm back at the start, and then I started, and then all of a sudden I'm to the left of the start point. So there's a lot of things going on here. You gotta see, what does negative and positive position mean? What does negative and positive velocity mean? Again, this tells me how far am I from the start point. This tells me what direction am I going. If you want, you can also say this is the positive direction. And then this is the negative direction. Something that I have here. So positive velocity means I should be moving in the positive direction. Negative velocity means I should be moving in the negative direction, even if I'm over here. In fact, it'll be more accurate if I do it that way. Positive direction that way, negative direction the other. Are talking about, was it this one? Oh. Okay, yeah, so I just have to rewrite that real quick because there was something written on, but I can rewrite it in a second. So it was left, right, stationary. Again, stationary just is a fancy word for saying we're not moving. So left was 3.5 to 9 seconds. Right, we were 0 to 3.5. And then here we're at 3.5 seconds to be exact. As another way that you can think of this, if you imagine your house, for example, and your commute to school, for example. Let's say that you put your start point as your house. As you go to the school, for example, let's draw a dingy car. So as you go to school, your position is increasing from your start point, for example. Would this mean a positive velocity or a negative velocity? If you're positive, right? What about whenever after class in about a couple of minutes, you leave campus and then you go back? Is your velocity positive or negative? Negative. Now here's another tricky question. What if you decide you want to keep on going this way? Is my velocity still negative or is it positive? Negative, because we're dictating this as the negative direction. One last thing I want to note about this is that our choice of positive and negative is actually arbitrary because everything is relative to the position. In other words, we're defining what does it mean to be positive location or negative location for us. Because there's nothing that says I can't make the grocery store over here be the positive direction and the school be the negative direction. So all of our calculations here are, the signs are a little bit arbitrary so long as I keep consistent here. All right, so this is example 1, part A. I think we're going to be spending probably a week on initial physics application And then after that, we're going to do related rates application, the thing about like the engine piston and stuff like that. That'll probably take like the rest of the week after that. But yeah, lots of applications. We've just started our physics application section. Good news about these applications that the most important rules that you do know are your power rule and product rule. Those are probably the most commonly used ones. All right, besides that, that's all for today. Take some time to really soak in this part A and all the new terms that we just introduced. We will be spending quite a while on these applications. All right, besides that, I'll see you tomorrow.